Hi everyone, in this video we're going to get some help getting started with the activity that's due Sunday night. So what I'm going to do is I'm going to get you started with each of the problems. It is up to you to finish that problem. In number 1, we have a 200-pound person compresses a bathroom scale 0.40 inches. They tell us the scale obeys Hooke's law and want to know how much work is done if is done compressing the scale if a 150-pound person stands on it. So the first step, what we need to do first is to write our force equation, F equals K times X, and solve for that constant K that is for this spring scale here. Okay, so the force is the 200-pound person. K is what we are looking for, and the X, the distance that the scale compresses, is 0.40. If you divide both sides by that 0.40, divide by 0.40, we get that our constant K is equal to 500. All right, that's part 1. So now I know my force equation for this scale is F equals 500 times X. Now, the next step is we've got a 150-pound person standing on it, and I want to know how much work is done. All right, our work equation in this section is W is equal to the integral from A to B of our f of x, our force function, dx. A and B are how much our scale in this case is stretching. F is the force equation, so I could plug that in. That's the 500x dx. But we've got to do a little bit more work here to find out what the bounds of the integral are. The bottom bound, that's definitely going to be 0 because the person is stepping onto the scale. They're not like that. It's starting from a fresh position. There we go. But what I've got to do is take this equation a second time, substitute 150 equals 500x. To find x, that's the amount the scale is stretching. That's the top bound B. So if you divide 150 by 500, you get 0.3 is equal to x. And that x is the top bound. So bottom bound 0, top bound is 0.3 inches. If you evaluate that integral in your calculator, boom, done. Now, when you get to number 2, let's move this up a little bit here. We've got a spring balance this time. It's 10 inches long, and when there's no weight, if you put a 5-pound weight on it, it's 12.5 inches long. So I don't know if you can do this math in your head, but that's a stretch of 2.5 inches, from 10 to 12.5, 2.5 inches. Part A wants us to find that force equation, find the force necessary to stretch the spring. So F equals K times X. The force is 5 pounds. The K is what we're solving for. X is 2.5. That's the 2.5 inches that it stretches. If you divide both sides by, there's a decimal point there, by 2.5, let's see, this is 5 divided by 2.5 is equal to 2. Of course it is. So K is equal to 2. Our new force equation, F equals 2x. I'll leave part B up to you. I'll just say you integrate your function over the bounds of the integral, and it's stretching 2 inches from its resting point, so that gives you information, the 2 inches and the resting point. That gives you information about the bounds. You set up your integral just like I did in number 1. Then for part C, same kind of question, but we're stretching it from 11 inches to 15 inches. So we're stretching a total of 4 inches, but not from its resting point, right? So if the spring, it starts out, let me write this down, the spring is 10 inches long. We're given we're given that the spring is 10 inches long at the beginning of the problem. So if it's stretching from 11 inches to 15 inches, that is giving you information about the bounds of your integral, right? And I'll leave it up to you to figure it out, but you plug in the top bound, you get your top bound and bottom bound, evaluate that integral, boom, you're done. Okay, in number 3, we have to integrate by hand using U substitution. So I'm going to help you out with the substitution step, and then it's up to you to finish the rest of the problem. All right, so we've got a tangent here, we got a secant here, this guy's cubed, the one's squared. We're going to set U equal to just the tangent of x, because remember, tangent cubed x means parentheses tan x, close parentheses, raised to the third power. So if I set u equal to tan x, that's going to be a u to the third power, and we can use our regular power rule. Then du is equal to the rest of the integral, secant squared x dx. Boom. So that's the u substitution part. We have u to the third power du. I'm not going to write that down, but hopefully you were listening and can write that down. The other step that I have to take is rewrite my bounds. So I need to take and split up what is the tangent of the top bound. That's a calculator question. And what is the tangent of the bottom bound? That can also be a calculator question. All right, so do those in your calculator, make the substitution, and then antiderivative, plug in the bounds. Boom. Cool. Moving down to number 4, we have a function, breathing is cyclic and a cycle takes about 5 seconds, a function that models the amount of volume of air in the lungs at any time looks like this guy. Oops, meant to underline it. Looks like this guy right there. T is our time in seconds. F of t is the volume in the lungs. We have to set up an integral to find the average volume. That's that YAV formula of inhaled air during the lungs in one respiratory cycle. So the formula is the integral from a to b of f of x dx. You integrate your function, but you divide by b minus a. Excuse me, b minus a. So b minus a in the denominator, 5 minus 0. One cycle takes 5 seconds. From 0 seconds to 5 seconds, that's one cycle. You could technically do 5 seconds to 10 seconds, but you should get the same answer. Okay, and then bounds of our integral are also 0 to 5. The function is the function in the problem, dt, and then can you punch that into your calculator? That's it. All right, that's part A, is writing down that integral. Part B, use your calculator, push everything correctly, and then write down the answer that it spits out. That's it for this video. Hopefully that was enough to get you started with each and every problem. If you took the time to listen, thank you. I hope it helps you to ace this assignment. Have a great day.